Hello class, so we are going to be going over vector subtraction and relative velocities, which is a little bit of an introduction to frames of reference today. So to start off with vector subtraction is what we often do when we're finding the change in vectors, because hopefully we remember that change is the function of subtracting, or it's finding the difference between two things. It's functionally identical to vector addition, except you subtract instead of add. To visualize the subtraction, use your tip to tail method, but the deal is that when you're subtracting a vector, your subtracted vector flips its direction. That just makes it negative, right? It's the same thing if to think of this algebraically. It's like adding the negative. So you just add them, but you flip it, you make it negative. So you add the negative. Let's take a look at this visually. So here we go. I have two vectors. I have an initial velocity vector and a final velocity vector. For me to find the change, I want to take the final velocity subtracted by the initial. So this is the two vectors as they are. If I want to subtract them, I need to do Vf minus Vi. So I'm going to take the negative of Vi by flipping it. We can see that Vi looks completely identical. It's the exact same size, and it's the exact same slope here, except instead of heading up and to the right, it is heading down and to the left. It is negative of that. And now I can just tip to tail these two, and it would be Vf plus negative Vi, which is the same thing as Vf minus Vi, and that would equal my resultant, or my change in velocity. You could use trigonometric ratios or whatever you need to end up solving for those now. Let's do an example with some numbers. So we see we started with an initial velocity that was 2 meters per second and an angle that seems to be 32 degrees above the horizontal. But we ended this motion with a velocity that is 1 meters per second directly vertical. So to do this, step one, I go from my initial vectors and I change my initial velocity vector into its negative. I change that arrow. Then I tip to tail them together here. Now that I have this triangle, I can begin doing things. I notice that I have some information about angles and sides. I can begin analyzing this. One thing for us to note here is that this 32 degrees is measured in reference to the x-axis. Notice how that x-axis doesn't actually line up with our resultant vector. So we can't use 32 degrees as this angle between negative Vi and Vr, because it isn't. That 32 degrees goes all the way down to the x-axis. But you can see I can extend my x-axis and extend my Vf, and this actually makes a right angle triangle. So this allows me to actually use the rule that all the angles in a triangle add up to 180 to determine what this is, which is 58 degrees. So I'm going to use that, and I'm going to redraw my triangle, getting rid of this 32 because it's no longer inside the triangle, and writing it up here. There we go. Now that this was rewritten, we have this 58 degrees up in this corner. We know the size of negative Vi, and we know the size of Vf. So we have side angle side. This is a thing for cosine law. So we can determine the magnitude of Vr by using cosine law. And I've just plugged it in here. Now we can use sine law to determine the angle of Vr. Now just a little thing to note. This drawing, you might look at that and be like, hey, it looks like Vr is close to 90 degrees. I might run into an ambiguous case of sine law. While I would totally see where you're coming from, this is not to scale at all. And if you take a look at the values, Vi is 2 meters per second and Vr is 1.98 meters per second. Those are almost the same. So this is almost an isosceles triangle, meaning this drawing is definitely not to scale at all. If this is almost an isosceles triangle, the 58 degrees here should be very similar to the phi that we see here, phi representing the angle between my vertical Vf and Vr. And a little bit of sine law showing our sine law shows that that's actually the case. Yes, so phi is 59 degrees. So that's nice. This phi is also measured versus this y-axis. So I actually don't need to do further conversions to compare it to an x or y-axis because it's measured on VF, which is totally vertical, which is the y-axis. So I just get to use that for my answer now. The resultant velocity is 1.98 meters per second at 59 degrees left to the left of the vertical. Is my drawing very good? No, it is not. But it doesn't need to be. We have cosine law and sine law to make up for that, for our inadequacies there. So using component method is the other method that we've been practicing. It doesn't require us to visualize quite as much, and when we use vector notation, it tends to tidy up real nicely. So let's take a look at this example here. Jim is initially biking at 3 meters per second east, but he turns a corner and is now biking at 4.3 meters per second at 21 degrees east of north. What's Jim's change in velocity? We see this term change in velocity, and that makes us think we have to subtract final minus initial. Like we've been doing with components is we still start out by drawing our initial vectors. Here's VI, it's 3 meters per second to the east. Here's VF, it's 4.3 meters per second at this angle 21 degrees east of north. I'm going to use my sine and cosine ratios to determine the magnitudes of these x and y components. VI is nice because it is all x component, no y component. So that's convenient. So my function is the change in velocity is equal to the final velocity subtracted by the initial velocity. When I have it in my vector notation method, we see that the change in the x component and the change in the y component would be equal to the x component of VF subtracted by 3 and the y component of VF subtracted by 0. So do that little subtraction, and the x component of V, the x component of the change, is negative 1.46, or negative, in this case we see is going to be west because we've chosen all of our east values to be positive. And the change in y is 4.1 positive. We define that as north. I didn't say it explicitly before, but you can check back and see that that's what we did. So now that I have my x and y components of my change, the next step is simply to make a triangle of it. Right? Here's my x component, here's my y component. This is the resultant. Use a little bit of Pythagoras to solve for it, and use a little bit of trigonometry, SOHCAHTOA, to find out my angle. Here is my end result. So the next thing for us to discuss are relative velocities. This relies on the principle of superposition. Now, to say this relies on the principle of superposition implies that other things don't, and that's simply not true. The principle of superposition is a fantastic elegance of all of physics here. So let's go over what it is. It says that any set of the same type of vectors on an object can be described as a singular resultant vector. And the singular resultant vector is the sum of all of that type of vector that are acting on the object. A way to describe this is perhaps you can think of somebody does many different displacements. They go here, then there, and back and forth, and this and that, and they can have many different displacements. But you can consider, well, if they started at one spot, and after their many motions they ended at a different spot, you could just say there's one final displacement from where they started at the very beginning to where they ended at the very end. There's only one end result, and how can you find that is you can simply add all the pieces together using vector addition. This works the same with any set of vectors that are all the same. So if you chose one of the people in the class and everybody chose to apply a force on that person, everybody's going to be applying forces of different magnitudes and forces of different directions. And yet that person is a singular mass of molecules. That person will only end up going in a singular direction. So what direction will they be experiencing their acceleration? caused by all of these 20-some forces? Well, it would just be the vector sum of all 20 forces. Simply add all forces together. This means for a situation that may seem as complicated as having 20 different forces is actually, while maybe not easy to calculate, is easy to understand. If you know the interaction from one piece to the next, then you know how all the pieces interact. You simply have to add all the pieces, which means you need to know all the pieces. But the understanding is simple, even if the application can be a little complicated. And this is a beautiful thing that applies to all of physics. We're going to use it explicitly when we're dealing with our relative velocities, which is going to be talking about viewing things from a particular frame of reference. So if I were to relate this to a boat and river problem, when you're observing a boat from the shore, the boat has its own velocity that it's capable of, so there'd be boat velocity. But the river provides its own velocity that it would drift the boat along. So there are two velocities on this boat at the same time from the perspective of a person on the shore. The result of these velocities would be the simple addition of these two vectors. So let's look at a simple example, and I'm not going to go through the calculations. I want you to try the calculations on your own. So make sure to pause before I flip to the answer for each time. So looking at this situation here, we have a motorboat that is traveling 4 meters per second east and encounters a current that is traveling 7 meters per second north. First up, what's the resultant velocity of the motorboat? This is asking, from a person on the shore, where do they see this boat going? So add the two velocities, create your triangle, add them together. Take a pause, find out the answer. Hopefully you took the pause. The answer is 8.1 meters per second at 60 degrees north of east. If the width of the river is 80 meters wide, then how much time would it take the boat to travel from shore to shore? Now, the current of a river is, in most cases, perpendicular to the width of the river, right? The current flows in between the banks. So the width is measured from bank to bank. The current would be perpendicular to it. So this 80 meters is an east-west measurement because our current is traveling north, right? And so perpendicular to north would be east-west. So since this is an east-west measurement, the only velocity that actually is going to determine east-west movement are east-west velocities, perhaps the velocity of the boat. So use that to determine how much time it takes to travel from shore to shore. You probably don't need that much time, so hopefully this is going to be a very short pause. The answer is 20 seconds. And then if we consider what is the distance downstream that the boat reaches when it gets to the opposite shore, in this case, now if I'm talking about downstream, I'm talking about up and down river directions. Up and down river is a north-south thing. So we would consider using our north-south velocities, and we have just been given a scalar value, time. We've just solved for a scalar value. So we can utilize a scalar value in both sets of east-west and north-south because it is direction independent. It's a scalar. So that's a nice thing. Take a pause, solve this one. Hopefully it'll go quickly. We see that the boat should reach the opposite shore 140 meters north of where it started. 7 meters per second north for the current for 20 seconds of acting. So 7 times 20. Now, those problems were pretty straightforward, and hopefully you found them pretty easy. This problem here is a really common style of problem that utilizes a very specific wording, and it makes you think about the goal is to make you think about what I am actually asking for. So let's read the problem and find out. An airplane is flying 33 meters per second, and it must move due north to reach its destination. There's a tailwind blowing at 12 meters per second at 24 degrees southwest. What heading must the plane actually take? Now note, our movement due north is what we want. It's the result that we're looking for. When we say it that way, we're like, okay, that means V resultant, should actually be directed due north. I'm going to draw the situation so I have my resultant vector due north. There, start, end, due north, that is my resultant vector. As we've been practicing, we see that the velocity of the airplane plus the velocity of the wind, these vectors should add to make VR. So I need to create two vectors that add to make that result. The easiest way to start is to start with the thing that you know. We know about the wind. So I will start by adding the wind from my start onward. There we go. I've added in my wind vector. It's 24 degrees south of west and has a magnitude of 12. So I need to, from the tip of my wind vector, add a vector that will reach to my end. There it is. And we know the magnitude of this one because we've stated that the velocity of the plane is 33 meters per second. With this, hopefully we can now begin putting together our angles, and we will be able to actually solve this one only with a set of sine ratios and a little bit of extra geometry. I want you to take some time, and I'll provide the answer later, but if you're not sure on how to solve it, talk to the people around you and try to figure this out. Okay, I'm going to post the answer now. It is 19.4 degrees east of north. Hopefully this was making sense to you, and we'll have more time to cover this again when I'm back in class. Have a good day, everybody.